I'm sharing the screen. Okay, so thanks for joining. And so I am thinking about how to structure these the best. So there are practice problems that we essentially have posted. And I was hoping that we essentially could start off with some of the more specific questions. So who on the call has some specific questions? I would very much appreciate if we could start off with some. Yes?
I had a lot of questions, but they were very much explained by the answer key, actually.
Okay, so that's good.
Yeah, I was very thankful for that. And
okay,
I guess that's it. Sorry, go ahead.
Okay, no, that's fine. So I would then, if nobody else on the call has a specific question, so Ayana, I saw you go unmute.
Yeah, and this may or may not be a question you can answer because it's not very specific, but I've noticed as we go through some of the different sections that they jump from talking about the sampling distribution back to just a point estimate, and it's just super confusing, I think, to try to help you understand what I mean. Like if we're looking at a confidence interval, are we looking at the confidence interval as a sample distribution, or are we looking at it as a point estimate? It just gets jumbled.
So a confidence interval, by definition, if I just may pick up on that, the confidence interval is an interval, so to say, right? So essentially the way you have to look at this, and I think this is a good depiction in this context. So you all can see my screen, I hope.
Yes.
Okay.
Yes.
So we're seeing here a population, right? The population has a very wide variability, which goes around the true population mean, which is here 100. So a good way to think about a confidence interval in this context. So you have here the sampling distribution. So that's the distribution of the sample means. That means that this distribution is essentially not the population, but it is the result of the distribution of repeated sampling from the population. So you essentially, you get with each sample that you draw from the population, you get one sample mean, and this sample mean, particularly with large sample sizes, and this is part of the central limit theorem, is essentially an estimate of the population mean. So now when you are calculating based on a given standard deviation, and this is the case for when you have the standard deviation given, you essentially, you get this standard deviation and you use the standard deviation to relate the standard deviation of the population to the variability of these sample means. So think of the distribution of the sample means of repeatedly drawn samples that essentially have one sample mean, and that sample mean, each of these sample means is not exactly the population mean, but it kind of deviates around something. And if you get the mean of these sample means, essentially you have a very accurate measure of that population mean. And if this is done with large samples, you get a mean that is even closer and more accurately reflecting this true population mean. And your confidence interval or your standard error of the mean is essentially the distribution or the variability of these means, of these sample means around the true mean. So what you're doing essentially when you look at one sample, you are taking this given standard deviation from the population and you're basically relating it. Wait, let me find the slides. I didn't develop the slides, so I need to find this myself. But the context essentially is, that's a nice one. So essentially you have this repeated samples here. So you have simple random samples, and all of these will have essentially a confidence interval, which is calculated from this given population standard deviation. So based on that, you're building up the standard error of the mean that you would assume essentially reflecting the variability of the sampling distribution of these sample means in the sampling distribution. And if you are taking now the 1.96, for example, you can calculate a 95% confidence interval around your sample mean, which is the point estimate. And this 95% confidence interval from the upper limit to the lower limit will essentially provide you with a 95% confidence that within this interval, you will find the true population mean.
Okay.
Does that make the difference between the point estimate and the confidence interval clearer?
Kind of. So that confidence interval is still the distribution, or it's just one?
It is one sample that reflects, based on the known standard deviation of the population, the expected distribution of the sampling means. If you're drawing repeated samples based on this sample size.
Okay.
So you have a known standard deviation. I'm trying to find the standard deviation. Okay, we have where is this slide? Okay. So we have essentially, we have a known sigma. We have a known, oh no, that's, yeah. So this is an N. So we have a sample of 712 individuals. We have a known population standard deviation of 40. And we are calculating a standard error of the mean of 1.5. This means that this X bar of 183 pounds is 1 point estimate, but based on the variation that we know, the variability, the standard deviation we know from the population and from the sample size, we expect that variation, that standard deviation of the sample means around the true mean, the true point estimates that we have at hand from our sample, to essentially be between 185 to 185.5. So within that interval, with a point estimate of 183, we have a 95% probability to capture the real population mean.
Okay.
Okay.
Mm-hmm.
Makes sense. Okay. So now this is important as a concept, because essentially it relates, and this is what the central limit theorem does. And I'm trying to find this slide now. The central limit theorem basically has. Here we go. Now that's the proportion. Yeah. So essentially relates this population variability to the variability of the sampling distribution. So you essentially are gaining confidence about that true estimate of that point estimate. And by that, essentially the sample size will determine how much variability you will find in this estimate, given that it has a certain sample size. So if the sample size is smaller, there will be more variability, because your estimate of the true population mean is not going to be as accurate. If you have a high sample size, it's more likely to be closer to the mean, which is part number one of the central limit theorem. And part number two is that the relationship between the sigma, the population standard deviation, to the standard error of the mean is basically sigma divided by the square root of the n. This basically is the second part of the central limit theorem. The third part would be that you even can draw from a skewed distribution and still get a normal distribution for the sampling distribution, which is also important knowledge, because you still can use parametric methods, although the original scores in the population distribution may not be as beautifully normally distributed. I hope that makes sense conceptually.
Yes, much more sense.
All right. Glad to hear that. Of course, of course. Any other questions? So thank you for this question. Please ask more. Ask yourself away. I'm all yours. Any other questions on some of the concepts? Otherwise, we could essentially start on doing some of the calculations, which we have here, this wonderful spreadsheet that Professor Johnson has prepared, where essentially we can put all these numbers easily in and can calculate them quite automated. Do we want to do that? So if we have a mean of a population, so let's start with the first example. So we have a mean of a population that is known to be a mu of 160, and the standard deviation of the population is known to be 18. So again, this is we have a true mean. We know this mean, and we have a standard deviation, right? So this is essentially an example where we need to understand the set scores and how the distribution of a population looks like. So essentially, when we have now a true mean of 160, and we have a standard deviation of 18, and a sample size of what would be the, okay, we can't really calculate. Okay, so but this we could do easily here. So we have here now. Okay, I have an Excel spreadsheet open here. So if we have a mu of 160, and we have a single observation of 142. So essentially the formula would be that we are taking the 160 and subtracting them from 142. And we're dividing them by the sigma, which would be 18. So that gives us, let's do mu 60. We have a sigma, which is 18. So we're getting, based on that, we're getting a set score of -1. So if we're going to see a set score of -1 on the set score table, which OpenIntro is essentially providing you, we are basically, and we can also employ the empirical rule as suggested as per the spreadsheet. But if we have -1, we have to the left of this set score, we have 16% of the population, right? So this spreadsheet essentially, this set score table essentially starts here with 0, goes all the way to 0 up to 50%. This is the mean, and everything greater than that is essentially then spreading up to 1. So essentially, what you need to do is nothing else to essentially look to the left of that point that you're calculating. So when you have now 166 as the second example, that was the point estimate of 142. So that was 1.1 set of 142. So this is a set at 142. So if we do 1.2 and our set, we want to have the set for like that. So we have here 142 as a score. We're doing here a set. And we're taking now 166. It's basically, it follows the same scheme. So we're doing the actual score, 166 minus the mu divided by the sigma.
Are you able to zoom in on your Excel spreadsheet?
Yes, I am.
Thank you.
Okay, sure. That's better. Okay, so I open this. Oh. That better?
Yes.
Okay. So now we have a set of 0.33. So this is now on the set score table. Essentially, you go to positive 0.33, which would be here, right? So we have 0.63 or 6293. So this being said, so here we said it was 16%, 0.16 as per the set score table. If we have 0.33, we said here we're seeing now 0.6293. 0.6293. Okay, you can of course also approach this programmatically, but I think since this is more of a systematic question, I think it makes sense to really read it from the set score table. Okay, so now we have between 142 and 166. So now you want to essentially have the difference between that. So now you want, so 1.3 would be in between these two, and that would basically be the difference between this minus this, right? So this is the difference that you have in between. So this is 0.47. And that's essentially how you would approach this. Does that make sense so far, right? So this is a simple one. If you carry on now, you go to example number 2. So now you have a random sample, right? So you have a sample that has an n of 36. You have a mean of, and sample mean, notably, of 165. And you have a standard deviation of 18. And this is where we're coming now in the realm of confidence intervals. And this is where we could use actually the confidence interval calculator. So here we come to 165. Now we have a sigma of 18 and we have a sample size of 36. And this confidence interval estimator will essentially give us all the data that we will need. So we have now calculated through, we have here the standard error. So our standard error is 3. The 95% confidence interval, assuming, so this assumes a set score of 1.96, right? So this is essentially, and this is also what the answer key will provide. Essentially, it calculates now the X bar minus this standard error of the mean multiplied by 1.96. Or for the upper limit, it will basically add it to the X bar. So essentially, you get now this interval within which you have 95% confidence that the true population mean is located in. If you are now decreasing your confidence, and you're basically, you're increasing your confidence, and by that you need to widen your interval, because if you have a wider interval, you're more likely to capture the true population mean, right? So you have this situation that now if you have a standard error of the mean, where's this now? So yeah, if you extend the standard error of the mean and this confidence interval, so either it changes the standard error of the mean, or you change the set score with which you essentially defining your confidence. If you widen that, you're more likely to catch this population mean that is somewhere hopefully within this interval. So essentially, if you go to a 99% confidence interval, you have a wider interval. So this is now, the calculator gives you the answer for this question, where you basically have 157 to 173. In the same context, if you narrow your criteria and you're okay with only 90% confidence, you are decreasing your set score with which you multiply your standard error of the mean. So now you're basically looking at 1.645. And if you look for these numbers on the set score table, you essentially get with 1.65, you get here 1.64, 1.65, you get here 0.9495 and 9505. In between, you have your 5%. 5% on both ends gives you 10%, and this is your 90%. When you go for 1.96, as mentioned before, you're actually at 2.5%. 1.96, you have 0.9750. Again, two-sided, and you have 5%. So this is 95%. If you go to 2.58, you're coming to 0.995, which essentially translates in 0.5%. Both sided again, you had 1% and you have 99%. Does this make sense so far? Any questions to that? I think that's considerably easy, right? But these are the differences between a point estimate, which is the sample mean essentially, and your margin of error or your confidence interval, both sided. So if you have now a random sample size of n equals 15 and an x bar of 150 with a standard deviation of the sample. So this becomes a little bit more tricky because when you have a sample, you are essentially using not the you're not using the set distribution anymore. So now you need to use hypothetically, although the answer key doesn't ask for that, but if you have a standard deviation, assume the non-population a random sample. Okay, so we did this one. We have now this one, 150. Assume the standard deviation of. So we did this one. So we have now 36 as a mean. A random sample size of n36 has sigma of 30. Assume the population normally distributed. We have 36 sigma 30, and we have our x bar is 150. So now this essentially goes in the same direction, this question, right? So we have, again, we have 140.2 and 159.8 for 95. So the standard error is given with 5. So this is essentially how you would approach all these questions. You have here a 99% confidence interval where you multiply your standard error of the mean with the 1.645 and oh no, the other way around. And no, 1.645, and here you would multiply it with the 2.58. So essentially that's how you get larger and smaller estimates. And if you're coming to the next question, where you have a random sample size of n15, and now you really you need to go now into the t-distribution, and this is also provided here. So we have now 150. So we have an x bar of 150. We have a sample size of 15. And we would delete this. Okay, well, the sigma is not known and small sample size. So we have now the t value. Okay, we have a standard deviation of 30. With a sample size of 15, we have an x bar of 150. So the difference now is that essentially we need to estimate now our standard our t-score that we will need to be using. So if you go to a t-value, and you've seen this, let me try to find it. So we have now a t-score table, a t-distribution table. So we have a degree of freedom, which is always n-1. So we have an n of 15, which essentially gives us a degree of freedom of 14. And now you will always assume two tails. So two tails essentially is here at 5%. So if you go here for 14 degrees of freedom of 14 with a two tails alpha of 0.05, you essentially have 2.14. 2.14 here gives you 95% confidence interval of 133.39 and 166.61 based on degrees of freedom of 14 and your known statistics of your sample. So in the same fashion as for the set score, you also have here given the 99% confidence interval, which is essentially wider and capturing with a higher probability your true population mean. And you have essentially here a narrower estimate with the 90% CI. And this is again the two, and it's not the 2.58 from the T-score table. You would read this from. You would read this essentially from this level. So you would multiply it by the 2.98 and the 1.76 for the 90% confidence interval. So with two tails, you have your 10%. And for the 99% confidence interval, you have an alpha of 0.01. Does that make sense so far? Any questions on the differences between set distribution and T distribution? So the difference is really that you do not have the real standard deviation given of the population, but you're estimating the standard deviation from the sample standard deviation. If you're going now further to example number 4, we have done this one. 3A. Now we went through this and this. So now let's talk about 4. So we are having now average weight of an adult male in DeKalb County, Georgia. We draw a random sample of 1,000 men from a population of 1 million men and weigh them. We find that the average man in our sample weighs 180 pounds. So the difference is also that the T distribution essentially is relevant if you don't have the standard deviation given and you do not know the population standard deviation and it's a considerably small sample. As soon as you have a large sample, and this is what's given here, and the threshold is, I don't think there's a really clearly established threshold as far as I know. I know from previous lectures from Professor Waldron that the threshold is somewhere at around 30 sample size. So I've been told that after 30, you're kind of on the safe side if you assume a set distribution rather than a T distribution. So if you look here, for example, we had for the set distribution, we had for the 5% confidence, 5% alpha, we had 1.96. So this was 30 still at 2.04, and it keeps on decreasing down to 1.96 with 500. But however, everything that gets above 30, you kind of get away from using set distribution rather. That's what I've been communicating. That's what I've been working with in my professional life. So essentially we have the T distribution as not being necessary, so we can work here with set distribution. So we have a 95% confidence interval for the average weight of men in DeKalb County. So we have, again, we're going back to the confidence interval calculator. So we have the average man in the sample weighs 180. We have a sigma of 30 with a sample size of 1,000. So now the 95% confidence interval would here be 178.14 and 181.9 as the upper level. So again, the point estimate is here 180. We have the 95% confidence interval going from 178.1 to 181.9. If we are decreasing the sample size now by 100, and the answer key is quite clearly reflecting that if the sample size is decreasing now, essentially our confidence interval essentially is changing now from 178 to 189 to 174 to 186. So it widens. because essentially exactly what I meant here, if the standard error is wider and you're multiplying it with a Z score to get this confidence estimated, you narrow the standard error with an increase of your sample size, because the variability of your sample means is going to be less in your sampling distribution. So for that very reason, you essentially get here a less accurate estimate with a smaller sample size. So therefore, the confidence interval widens. Does that make sense so far? Any questions on this? Okay. So now we have a major metropolitan newspaper surveyed a random sample of 200 voters. They asked whether they planned on voting for a new bond account on the 10th. Of those surveyed, they said they plan to vote yes. What is the margin of error for this estimate? So we have now a P. So this P is essentially 110 out of 200, right? And now the 1 minus, so this would essentially be, so this is where we need the second worksheet. So we have 110 successes out of 200 sample size. So this is a P cap of 55%. So now the calculation is essentially just like shown here. I'm zooming in a bit. The calculation is here essentially the standard deviation estimated as the P of 0.55 multiplied by 1 minus 55, which is 0.45, divided by the sample size. So this leads square rooting that essentially gives us the standard error. And under the law of large numbers, we can, under normal approximation, we can essentially now build a confidence interval around our proportion estimate. And this follows the same principle. Then essentially we have now discussed with our normal distribution with continuous variables. So if we are now going in the same example, no, that's not it. No, that's hypothesis testing. So if we have a normal approximation, we essentially we're estimating the 95% confidence interval, because the estimate of a proportion essentially follows the same dynamic than it does with a continuous variable. So you get with repeated sampling, you get an estimate of the true population proportion. So if you repeatedly sample and you get sample and you calculate the proportion of yes voters within that sample, and you're taking 100 different samples of the same size, you will get a certain distribution of each estimate. And this will, just like with a continuous variable, essentially distribute in the shape of a normal distribution curve. And therefore, you can essentially use the same principle. So you estimate the standard error of the mean, which is the standard error of this proportion estimates. And by that, essentially, you can also use the same principles to estimate the 95% confidence interval, within which you are 95% confident that you get the true proportion of the population. So for our example here, with 110 yes voters, with a sample size of 200, assuming a proportion of 55, you are certain from 0.48, 48%, for 48.1% to 61.9%, within that 95% confidence interval, you are actually certain that you will be capturing the true population proportion of yes voters. So this is also that margin of error that is basically reported as you see it on the mean on the news. So this is essentially how this is being estimated. I hope this makes things somewhat clear. And those were essentially all examples that were given in this context. So are there any questions on either of these examples? Okay. If no further question, then I'll turn off the recording for now. And hope this was helpful.
Yeah, it was.